Yeah, so today we're actually gonna start using entropy for something. Couple things I wanted to just write down again. These are gonna be important. The chain rule and like, I guess I'll call this the deconditioning lemma. Maybe I'll write this in a more general way than I did last time. So generally speaking, if I've got some random variable x, oh, sorry, let's take a step back. So let's say, let's suppose S is a subset of T, which is a subset of numbers 1 up to n. Then if I take some random variable x, conditioned on, so I'm taking the entropy of it, conditioned on x I for all like I in S. So all I mean is like we're taking the entropy of x, the conditional entropy given all the variables xi, where I is an element of S. That should be basically if I'm conditioning on fewer, it's like S is a subset of T. So sort of like if I'm conditioning on fewer things, the entropy should be higher. So yeah, and this is like for any random variables x and y I for I between 1 and n. And all this is saying again is if I've got less prior information, so like if all I know is the outcome of the random variables for I and S, then when I learn the outcome of X, the amount of information I gain is going to be, at least as large as if I only knew less information, or sorry, more information. If it's going to be higher than if I had known more prior information. Okay. Let's use this to prove Shearer's lemma, which is kind of a useful tool involving entropy. We take an integer t at least 1. And let's take a family of sets, family of subsets of 2 to the n, such that every element of 1 up to n is contained in at least t of the sets in F. We've got a set system F that covers every point at least t times. So then for any random variables, x1, x2 up to xn. So the entropy of x1, x2 up to xn is at most 1 over t times the sum over all the sets F in curly F of the entropy of the random variables xi, where I is an element of F. maybe like as a little example. So imagine this is like my set system app. Oh, and let's see that as well. Oh, let's see. Right, let's say, so each of these like blobs is like a set in my family, right? I've got T is 2. I think if you check, actually everything's covered exactly twice. So what this would say, what Shearer's lemma would say is that the entropy of, like, regardless of what these, doesn't matter what the random variables are, regardless of what they are, this is going to be at most the entropy of. So just go through your sets in your family, x2, x3, x5, plus x1, x2, plus x1, x4. So all this should be, maybe I'll multiply this by 2. Well, anyway, so this is all 1/2 times all of this stuff. And then what, 3, 4, 5? Okay. So let's prove this. Yeah, is the statement clear? Let's start by looking at T times the entropy of x1 up to xn. So by the chain rule, I can split this up in this way, right? So I'm going to write this as the sum I equals 1 to n of T times h of xi, given x1 up to xi minus 1. So I've just done the chain rule and I brought the t inside. So let's now use the fact that I know that, so in my family F, every I in N is covered at least T times. So what I'm going to do is I'll take, again, sum I equals 1 to N. And now I'm going to sum over all of the F in F, so F in curly F, such that I is in little f, or it's not little f, but I is in the set F. Entropy of xi given x1 up to xi minus 1. Okay. And the reason this is okay is because, like, this, I mean, this sum doesn't depend on the F. There's like, you know, T, at least T summands here, and they're all the same. So yeah, it's going to be at least T times that. Right? Okay. So now I can switch the order of summation. I think that's what I want to do. Yeah. So if I switch the order of the summation, it'll be like I'm summing over all the sets that are in F. And then I'm summing over all the I in that set. And taking xi given in xi given x1 up to xi minus 1. So maybe it takes a little bit of thinking to realize that this is indeed like the correct way of switching these sums, but it should count the same things the same number of times. Okay. Now what I'm going to do is I'm going to like drop some conditioning here, right? If I condition on fewer things, the entropy goes up, right? That's what this thing was trying to say, that if I remove some conditioning, the amount of information I gain should go up. So so this is like we're taking xi given all of the kind of variables with a smaller index. What I'm going to do is replace this with just taking all of the variables with a smaller index where that index is in F. So I'm kind of gonna, yeah. Well, so what I want is xj. So I'm conditioning xi on xj for all j which is less than I, and j such that j is less than I and j is in F. So like this thing would be, this thing is the same as conditioning on all j xj such that j is less than I. And this is like, only making fewer conditioning things, so the entropy should go up, right? But actually, if we apply the chain rule again, so I'm going to apply the chain rule to this thing. Think about it, what is this? So if I, for example, if I take the smallest element of F, so if I is the minimum element of F, this just computes the entropy of xi for that I. Then I go to the next element of F. This is the second smallest element of F given the smallest, and then the third smallest given the previous two, etc. So actually applying the chain rule in reverse gives us that this is precisely this thing. And that gives us what we wanted, because this divided by t, and that gives you the lemma. I would say throughout all of this, probably the two most important things to understand are like this chain rule and the deconditioning kind of idea. And really, like if you don't understand, like you'll probably never have to use the actual definition of conditional entropy. Really, the chain rule is the most important, thing that you'll need to use. Okay, so let me now state a corollary of this lemma. This is called Hans inequality. It says for any random variables x1 up to xn, entropy of x1 up to xn is at most 1 over n minus 1 times the sum for all j from 1 to n of the entropy of all of the variables xi such that I is not equal to j. And the proof is easy. You just apply Shearer's lemma where you let F be the set like n choose n minus 1 and T is n minus 1 and then just apply the Shearer lemma thing. Okay, so what I want to do next is apply this Hans inequality to prove a kind of nice result in geometry. This is called the Loomis-Whitney inequality. So let's let B be a subset of Rn. So let it be a open. I think you can loosen these, conditions a little bit, but for for all intents and purposes, let's just think of it as being open and bounded. But lives inside of a region of Rn, it doesn't go off to infinity. So for each j between 1 and n, let pi j be the projection of Rn to the plane, the hyperplane, where we just wipe out the j coordinate, just make it 0. So for example, if I take pi 2 of 1, -2, -5, it just gives me 1, 0, -5. This is, I guess, in the case n equals 3, right? So what I want to say is that the volume of the set V can be upper bounded in terms of the volumes of all of its projections. So let's use this to mean the volume in n dimensions, which is maybe technically the, I don't know, the Lebesgue measure, or let's not worry too much about it, but basically the volume of this set in n dimension in Rn is at most the product from k equals 1 to n of the n minus 1 dimensional volume of the projection of B onto the j, or onto this kind of hyperplane. So what I mean by this is think of this hyperplane as being Rn minus one, right? Because everything is zero, or the J thing is zero, right? And then you can just compute the volume in the usual way in Rn minus one, right? So you product over all of these things, and then we take the 1 over n minus 1 power. In 2 dimensions, it's kind of easy to see that this is going to be true. Here's the kind of picture, right? Imagine I've got some kind of blob in 2 dimensions, right? Some open set. And let's just think of it as one kind of region like this. And now imagine I project it onto the, onto the x-axis, project onto the y-axis. Right? And if you think about it, if I take this length and times this length, that gives me the volume, the area of that box, which obviously is bigger than the area of the blob, right? So that's essentially what for n equals 2, this is what that's saying is, yeah, I project, the area of the box that surrounds this thing is going to be at least as large as the area of the actual object. When you go to higher dimensions, it's a little bit, maybe it gets a bit more interesting. Because now what you're doing, let's say in 3 dimensions, you have this kind of body in 3 dimensions, project it, like take its 2-dimensional projections, compute their areas, then you multiply all 3 of them, and then you take the square root. But that's maybe like I think it's less obvious to think about why that should work than the 2-dimensional case. But yeah, it does work. Is this statement clear enough? If you're not, I mean, this is not a topology course. If you're not that comfortable with, say, open set, just think of like a blob where the boundary is not part of the blob, right? I mean, yeah. Okay. I want to prove this by kind of discretizing this, like kind of turn this into like well, something where I can have a finite kind of like a finite kind of random variable, and then taking a limit. So for, let's say for some integer k, imagine I take let, let's say ck be the covering of Rn with cubes of side length over k. Maybe I'll say a grid of cubes, right? I mean, all I'm saying here is, like in the 2-dimensional case, just take a really fine grid and cover the plane, right? So, yeah, so each element of CK is a cube. So in the two-dimensional case, I would take, you know, this would be, one of my elements of CK and so on. And I don't really care if these things overlap or whatever, like on the boundaries, it's not gonna make a difference. Okay. So, let's let BK be the union of all cubes in CK that have non-empty intersection with the set B. Essentially, what am I trying to do? I'm like, when you like learn about integrals, you learn about Riemann integrals, and like the idea is okay, let's just chop up everything into little, I mean, in some sense, they're like little intervals, which kind of is like the one-dimensional kind of idea of a cube, right? Chop everything up into intervals. Let's approximate our function with these kind of height, these kind of interval these bars basically, and then like take a limit as the intervals get smaller and smaller. That's what I'm doing here. I'm my BK. So if this is my like blob thing, I can hardly see it anymore, but like my BK would be all of the things that intersect my blob. It's some kind of a discrete approximation of the actual shape, right? And since this thing was open, so it's a very nice kind of set. It's not hard to see that if I take the limit as the side length goes to 0, so in other words, the k is going to infinity, the length of these cubes is going to 0. If I take the volume in n dimensions of BK, that should approach the volume of B. This is the same way that kind of Riemann integration works, right? But I also want to say that if I look at a projection of B, and I look at a projection of the cubes in BK, or if I look at projection of BK and a projection of B, I should also have this kind of limiting behavior. So it's not hard to see that. I think also, if I take the limit as k goes to infinity of the n-dimensional volume of the projection of BK, that should give me, so I'm taking the J projection, that should give me the volume, the n-1 dimensional volume of the projection of B. I guess it's not hard to see that either, right? Like if I'm talking about how long is this projection, like these cubes are going to be a pretty good approximation of that as k goes to infinity, right? Or the projection of those cubes. Okay. So this makes things convenient because essentially what I can do is prove something about BK, and then it will transfer directly to B. Because so our goal is to show that the same thing that I wrote over there is true, but just for BK instead of B. So the n-dimensional volume of BK is at most the product of all J, the n-1 dimensional volume of the projection, the J projection of BK, And we want to show this for all k at least one. Because if this is true for every possible k, then it's going to be true in the limit. Right, if I take the limit of both sides, it's going to be true, so. So yeah. And so this kind of turned this kind of continuous problem into a discrete problem that we're going to solve. We're going to prove this using entropy. You're all, any questions at this point or anything? So let's let capital N sub k be the number of cubes that make up the set bk. Let's remember what bk is, right? We had this open set B. We just tiled Rn with cubes. Bk was the union of all the cubes that touch B. And I'm just saying, how many cubes are there? So like here, in this example, you would just count all the shaded cubes, right? 1, 2, 3, 4, 5. You know, it's like, I don't know, 20 or something. So since we've done this based on like a nice grid tiling of Rn, like basically if I know how many cubes there are that touch or that make up bk, I know what the volume of bk is, right? So the volume of bk is just, okay, how many cubes are there? And then each of those cubes has volume 1 over k to the n, right? Because it's a bunch of, each cube is like 1 over k by 1 over k by 1 over k, etc. in size, but each cube has that volume. So I haven't introduced any random variables yet. So let's actually select a random variable. So choose a random cube from the set of cubes that make up bk, right? Like, in other words, choose one of these kind of squares at random and let x1 up to xn be the coordinates. So when I say random, I mean uniformly. Of its lexicographically smallest corner, right? So I don't know, pick a random cube, and then like if I pick this cube, then like I take each cube has some number of corners, right? 2 to the n corners. Pick like the corner of it that's over there, right? This lexicographically smallest corner. Well, yeah. Is that clear what I'm doing there? So can anyone see, based on like the various parameters we kind of introduced, like what's the entropy of this gonna be? Maybe it hasn't come up that, it hasn't really come up today, but we kind of talked about this yesterday. The thing is, like I've got, how many different outcomes are there for x1 to xn? There's capital NK of them. Because there's that many cubes, and like, so there's that many bottom left corners of that many cubes, right? So this has capital NK outcome, possible outcomes, and all are equally likely because I'm choosing it uniformly. So this is, because it's a uniform random, choice, it should have this entropy. We can also write it as log base 2 of, so just kind of putting that to the other side. It's k to the n times volume of bk. So here I'm just solving this equation for nk. Okay. So that's the entropy of this. So using this Hans inequality that we wrote down, well, and kind of proved, I can upper bound this by 1 over n minus 1 times the sum j equals 1 to n entropy of xi such that I is not equal to j. By the way, this, like, why am I upper bounding this, right? Like, I mean, now the thing is, this entropy, this is the thing I want to get an upper bound on in the end, right? I can now express this in terms of this entropy. So really, I want to upper bound this entropy by something. That's why we're doing this, right? And now I guess the question is, how many possible, I want to upper bound this quantity. So how many possible outcomes are there for h of xi such that I is not equal to j? So we can think of it in terms of this picture again. We're picking a random cube, picking a corner of it, like that corner, the most southwest corner. And then I'm forgetting the j coordinate. So it's like I'm, for example, like now this will be have two coordinates, right? An x coordinate and a y coordinate. Let's say I forget the x coordinate. So it'll just give me a number, like it'll just give me the height of this, right? So for each of these, I just lose the information about the x coordinate and I just know the y coordinate. So if you think about it, in this case, the number of possible outcomes for the y coordinate is literally just like based on how long is this? Like how many cubes is the height of this? And if I forget, in other words, or also if I forget the y coordinate, it's just like saying, how wide is this? Right? And now, of course, like different possible outcomes come up with different frequencies, right? Like I'm much more likely to get, if I take a random cube here, take the corner and then project it, like I only have one chance of getting that as my outcome, but I have a lot more possibility of getting this one. So it's like, it's not a uniform distribution, but it's you know, we can bound the number of possible outcomes, right? So I guess my answer here is, if you think about it, it ends up being, so in other words, when I talk about possible outcomes, what is, I'm really talking about what is the range of this random variable. And I would say the range as this size. Yeah, I guess where this comes from is similar to how I got this formula. But now we're kind of one dimension lower. So it's like, or yeah. Also how, where this came from, right? Like, we're now one dimension lower, there should be an n-1 and a volume n-1. If you think about it, I think this, it's not terribly hard to see this, but yeah. But now what I'm going to use is that if I know the size of the range, I can bound the entropy by just the logarithm of this. So yeah, for any random variable, the entropy is at most the log of the range, size of the range. So yeah, so just going to continue this thing here. This should be at most 1/n-1, sum k equals 1 to n log base 2 of k to the n-1. The n-1 dimensional volume of the projection, the jth projection of bk. I'm just taking the log of this thing because that's the size of the range. But then actually, if you just we're actually done. We'll remove it. Yeah. So if you use your kind of logarithm rules, what we get is that the n times the volume of bk is at most the product. With logs, when you add them up, you can turn it into products, right? This thing can go up into the exponent. So and you check all the k's cancel. And then you can just like, so then there just are no k's in this because they all cancel. And you get the inequality that we wanted to prove. And then of course, like, you know, as we said before, this is just for the bk. This is like the approximation of b, but then you just take a limit and it'll you know, apply it for B as well. Okay, yeah, so, I think this is all kind of a little bit of magic, but, yeah, any questions about this? Yeah, this is the inequality we wanted to prove, except there's a bunch of Ks, but if you do the algebra, you'll see that they cancel. Okay, so, yeah, then, see you guys on Friday, and we'll do something more combinatorial, less geometric.